All right, let's get going. So my name is Sydney Nader, and today I'm going to be walking through a lane line detection algorithm that I have developed in Python. So here we go. So first I'm going to walk through some of the functions utilized. So here first we can see the mask video function that applies a trapezoidal mask to the video, forming a complex polygon, and it really just helps focus in on those lane lines. So we don't want to see the horizon, cars 2 lanes away. It's not important. We only want to identify the lane lines, so it really crops that video out in a useful shape. Then the rest video will convert the video from BGR to HSV. That's just making the road more distinguishable from the lane lines. Blur video will account for high frequency noise, and then edge video will come in, detect steep transitions where we think it's an edged pixel of the lane line, and draw in those edges. Find lines function will find huff lines. We'll pass it through the edged video, and it'll calculate huff line values, which are rho and theta values where the line intersects. So these rho and theta values are very critical. They're utilized a lot during the rest of the code, and it really is the heart of the code in identifying the lane lines. Moving forward, this lane lines function will find points on the lane lines to prepare the user for plotting. So we can see some polar to Cartesian coordinate conversions here, and we can see 2 x points and 2 y points being calculated from those rho and theta values. Later here we can see the plot lines function, so it helps plot the lines. We use linear regression here, so y equals mx plus b. Slope is found using the values found in lane lines. Y-intercept also found using y equals mx plus b. Then these y values are where we want the height of the lane lines to be placed. And then these x values, again, calculated utilizing linear regression. Then the line is drawn. Here we have an average function that's utilized for finding the averages of arrays that are compiled and appended to over time, and that's just for smoothing purposes of lane lines. Then we have the mean function where it computes the mean of collected rho and theta values. So diving into our main function, we have the video. So it prompts the user to enter, first we have the user entering a 1 or a 2, indicating if they want to observe video 1 or video 2. Got a little error loop here. And then if video 1 is entered, the file name as well as the HSV lower and upper thresholds will be specified. Test video 2 had a bit of a yellow hue, so the HSV values utilized in the code are a little different. So that's really the main difference between video 1 and video 2 is the file name and the HSV lower and upper thresholds. Here, lines 89 through 92, we can just see some initializations happening, and then diving into the code, we can see the video being imported in red. The video is snipped so that we're really focusing on this dimensions, and then the mask is applied. So now, as well as these dimensions, we're focusing on the actual lane lines themselves. Threshold is applied, converting BGR to HSV. Video is blurred to reduce high frequency noise. Edges are detected. Lines are calculated using huff line transforms. Some more arrays are initialized for the latter part of the code. And now we're going to dive into identifying left versus right. So in polar coordinates, pi over 2 is 90 degrees. So if theta is less than 90 degrees, then the left lane lines have been identified. So, really just utilizing the knowledge between polar coordinates to determine left from right lane lines. And then, coincidentally, if theta is greater than 90 degrees, that is classified as a right lane line. Once those left and right lane line rho and theta values are appended into an array, now it's time to dive in and find some points that will be utilized to plot the lines. So using this same, first we calculated the average values to collect the left rho and theta values so that we're increasing smooth transitions, and then we do that as well for the right. Now we're looking at the mean left theta value. So if this value is less than 90, we know that we're observing the left lane lines, and now we are going to find points on the left lane lines by using the lane lines function that was discussed earlier. So this is just appending those x1, x2, y1, y2 points to arrays that will be used later to plot the left lane lines. And this is incorporating that history type averaging function that I discussed earlier. So this portion of the code is really to just increase smoothness of the left lane lines and right lane lines later in the code if there are skips in the road, if there's high noise frequency. It's just kind of utilizing that history and the averaging to ensure that the lane lines are still accounted for. All right, and then same thing for the right lane lines, and moving forward, again, this is used for smoothness. And then once those values are appended into arrays, we will plot the lines. So x1, x2, y1, y2, those correlate to the left lane lines, and those will be plotted in a teal color. And then x3, y3, x4, y4, those will plot right lane lines in a blue color. And then we will show it to the frame, and if Q is pressed, it will break out of the video and the script will end. Right. So now that I've walked through the code, I'm going to run each video and show what's going on. So here I am going to run the file. It's prompting me to enter 1 for video 1 or a 2 for video 2. If I enter a 3, invalid input, prompts me to try again. If I enter, invalid input, asks me to try again. Alright, so let's start into video 1. So in the beginning we see some additional noise there. Yeah, some lighting problems, just a little bit of high noise frequency due to the beginning of the video. And I'm gonna let this one play out. So this part here struggled with a little bit because there was some lighting change and some darkness from the shadow of the car, but playing with the HSV values and messing around with the within the canny function was, with the kernel size, was pretty helpful. And then I also did struggle a little bit with the right and the top right and bottom right components of the right line kind of fading off. So something that really helped me there was that here in the code, let's see where there's the negative 10. Here, the fine-tuning really helped out with that. So now let's move to video 2. All right, just testing the error again and clicking video 2. So there was a really large surplus of light in the beginning of the video, so it made it a little funky. Oh yeah, it's playing out. And then you can see the huff lines are kind of recalculating themselves, and as the road got lighter, the HSV threshold wasn't as effective when identifying the difference between the road and the lane lines. And then here you can see the noise from all of the lines to the right also kind of caused the lane lines to move in a funky direction. So I think making a tighter mask could help with that, but the video was a bit shaky, so if the mask was too tight, you risk losing some of the lane lines at latter parts of the video. So that was just kind of a risk that I felt wasn't worth taking. All right, so let's talk a little bit about what we just saw. So discussing in detail my approach to sensing the left versus the right lane lines, touched on it a little bit earlier in the video, but really utilizing what polar coordinates mean and tracking the angle was really helpful in this sense for me. So using that, if theta was less than 90 degrees, that's identified as a left lane line, and if theta was greater than 90 degrees, identifying that as a right lane line was super helpful, and did a really great job at identifying the difference between left and right. If I changed anything in the detection pipeline to enhance the performance of my algorithm, not necessarily. I think the one thing that was added was the averaging component. So just keeping some sort of history was super helpful because it was pretty jumpy if the lines weren't being directly measured, right? So say you have a road and instead of being like this, it's kind of like line, 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 and you have gaps of the actual gravel in between the painted on white lines. I had some problems with blinking, but then once I introduced the average into the detection pipeline, that was really helpful in just using the history of what had been happening and averaging most of the rho and theta values that are being tracked from previous points of the video, and then utilizing them to plot the lines. I think that being introduced was really different and helpful, and that's the biggest difference between, to me, doing this algorithm on an image compared to a video. So with an image, I mean, it doesn't have the biggest impact, you know, because things aren't constantly moving. But with the video, keeping a history was really helpful because things are constantly changing and you need to account for those changes as the video is changing, whereas an image is just pretty stationary. So I would say that that's been the biggest thing that enhanced my algorithm with the detection pipeline. For recommendations on how the algorithm might be improved, I definitely think a more sophisticated way of storing the history and being more selective with when to utilize the history would be helpful. A lot of points where the lines weren't tracking the best were when the road was really light, or there was shadows from other cars, or there were a lot of other lines. So finding a way to maybe, like, as we're tracking the color of the lines, to then change the dimensions of the mask with those changing like pixel dimensions to really make sure that you're just gripping the edge of the line. Maybe somehow correlating the mask function with the edged function. That could be really helpful, because then you're making sure that your mask is really only looking at and capturing those lines that are of interest of you. And something else that I struggled with was with video 2, how there was a yellow hue. And I know from dabbling in photography, a yellow hue can be, it can be turned into a more realistic looking video if a blue filter is applied on top of it. So maybe figuring a way in the software to compensate for hues based on the time of day, if it's raining, if it's cloudy, maybe just finding a way within the software, or somehow hardware coding it so you could set it like a Polaroid camera to cloudy, or fairly sunny, kind of sunny, partly cloudy. Maybe having a setting like that on the camera hardware, or incorporating that within the software would be really helpful. But yeah, all in all, I think that the lane line detection algorithm was a really interesting project to work on, lots of fun. I think it works pretty well. Yeah, I think it works pretty well. We could see from the videos that for the most part it was tracking the lane line successfully the entire time, and the main problems that I ran into were due to the road being a very similar color to the lane lines, or the yellow hue of video 2. Video 2 is where I experienced the most noise with the lane lines, kind of deterring from their actual performance. So yeah, I just want to thank you guys for watching this video, and if you're interested or have some questions, feel free to contact me in the comments. Thank you.